Who you looking at, huh?
Hi. Welcome. Yeah, today we're gonna have some fun today. We're gonna be talking about logistic regression and estimates and logistic regression because they're kind of tricky. So let's dive in, shall we? All right, let me introduce you to a fifism. Oh, if this is your first time, my last name is Fife, and a fifism or a Dustinism is something that I teach that may not be what other people teach. Basically, I categorize. So when you're building statistical models, we need to evaluate the evidence for our model. And there are three sources of evidence. This is the Dustinism. Number one, visuals. Number two, estimates. And number three, model comparisons. So visuals are obvious. What are estimates? So estimates are like slopes or intercepts or R squared or Cohen's d. Basically, there are numbers that give you a concrete description of what is going on. Like a correlation coefficient tells you how related two variables are. Or a mean difference is another estimate. It tells you the average difference between two groups. And then we have model comparisons. So those are like estimates in that they are concrete numbers, but they are specifically designed to evaluate between two competing models. So a p-value, for example, is a model comparison estimate. And when you use a p-value from a model comparison perspective, it basically evaluates the probability. The null hypothesis that it tests against is that the two models are identical. And if p is less than 0.05, then that tells you that they are not identical, and the more complex of the two should be favored. That's how I typically think about evaluating evidence, is in terms of those three categories. I'm going to look at visuals, I'm going to look at estimates, and I'm going to look at model comparisons.
Okay, but what if you have like a model that doesn't give good visuals?
Good question, yeah. Sometimes there are certain models that are really hard to visualize. Like a chi-square test, you can visualize the results of a chi-square analysis, but it's not very intuitive, and it's hard to interpret. Structural equation modeling is another one that is notoriously difficult to visualize, although see the link in the paper for different strategies that I've come up with for visualizing structural equation models. And mixed models are kind of difficult to visualize, and because you want to take into account the different clusters, and so usually what we end up doing is visualizing a few clusters at a time. Anyway, who cares? Basically, there are models that are hard to visualize. Or maybe you have another model that has like 15 variables. Yeah, good luck visualizing 15 dimensions at once. But we can also have problems with model comparisons. There are certain types of models that the model comparison numbers aren't very good. Like, for example, you can't get p-values when you have non-nested models. Or like R squared is another model comparison metric that I talk about. Although I suppose you could classify that as an estimate, but whatever. Change in R squared between two models, for example. Not intuitive how to do that in logistic regression because logistic regression naturally doesn't have an R squared. Although there are some people who have proposed different methods for computing an R squared, but I'm not going to get into that. No, so we might have difficulty with visuals, we might have difficulty with estimates, we might have difficulty with model comparisons, and we also might have difficulty with estimates. And that tends to happen when the estimates just don't make intuitive sense. And that most commonly happens when you get into like generalized linear models. And, you know, rather than tell you what I mean, how about I show you what I mean? So in the next part, I'm going to analyze a logistic regression and then talk about the estimates from a logistic regression and figure out some strategies of how to interpret what they mean. So let's step into R. I'm leaving on jet plane to step into my R script. All right, we're here. Yeah. So I'm going to require flexplot and tidyverse because I'm going to visualize things and I'm going to tidy some things. So I'm going to use the Avengers dataset. One of the variables is died, whether they died in the final Avengers Endgame battle. And all this is doing is it's converting it from, all this is doing is it's converting it from a yes and a no to a 1 and a 0 because R is dumb. Okay, it's not dumb. R, I love you, but really? It has to be a 0 and a 1? Unless I'm missing something, but when I ran this as a factor instead of as a number, it refused to cooperate. So I created a new variable called dead that is died. That is the past tense, or that is the present tense of the variable died. But more importantly, it's just a 1 and a 0 instead of a yes and a no. So the question I might want to ask is, after controlling for superpower and strength, what is the effect of willpower? And so if we were to fit that model, this is how you would do a logistic regression. If you want to know how to do that, I will leave a link in the description. And then now let's look at the variables one at a time, just to get an idea of what's going on. So if we look at willpower, and we look at a logistic plot like this, we see that in the red, that's what the model is proposing. So it seems to suggest that as your willpower increases, your probability of being dead at the end of the battle increases, but never reaches above 25%. By the way, what is willpower? I think it is a very clever metric. This is a simulated data set, but I'm going to pretend it's real because it's more fun. Willpower is the number of minutes you are willing to wait at the DMV. Because anybody who's ever, or the Department of Motor Vehicles. I guess when I grew up in Washington State, I think it was the DOL, Department of Licensing, whatever. How long you're willing to wait to get a driver's license. Because those are notoriously frustrating to wait for and have notoriously long wait times. So somebody's willpower can presumably be measured by how long they're willing to wait. And so we do see some predictive power, maybe. There is slightly slopiness. There is some slight slopiness. Slight slopiness, that's fun to say. But let's go ahead and look at strength. And if we looked at that, we see a much stronger relationship. So that's a way steeper curve. And it seems that the stronger you are, the less likely you are to be dead at the end of the Avengers battle. So it's the weak people who are getting killed, supposedly. By the way, strength, I believe, is number of pounds somebody can bench press. And that right there is like Thor or the Hulk or something. Although, maybe it's on a log scale because they could probably bench press way more than that. Anyway, moving on. Now, we've got one other variable in the data set called superpower. We would love to look at that, but you can't visualize easily in FlexPlot that. Well, I'll show you what you can do. You can't use the model to visualize it, but you can do an association plot. So I'll go ahead and do that. Actually, it's down here. I'm going to go died tilde superpower. And what this shows is this shows the difference from expected proportions. So this right here, under superpower, yes. So these are the superheroes, and their predicted probability is yes, and we see that the proportion is negative. So what is that saying? That is saying that the number of superheroes that died is less than we would expect if these two variables were independent. Likewise, we see up here that the number of superheroes who did not die was higher than we would expect by chance. So that's one of those situations that I'm not going to be able to address today. There are ways to plot it. This is kind of an indirect way, but of course that's not controlling for all the other variables in the model. So this is in some ways a misleading plot. We can't glean much from visuals, but we can look at predictions. And so right here, I'm just doing a quick thing. I'm generating a fake data set. Well, I'll just show you what it looks like. If I look at prediction data, it just shows the mean of willpower, the mean of strength, and then superpower, yes or no. And so it's going to give a prediction based on the logistic regression model for what happens to the superheroes versus the non-superheroes. And if I predict that, then we see that superheroes have a 36% chance of dying. Yikes! And then non-superheroes have a 10% chance of dying. So it looks like the superheroes were heavily targeted in the Avengers final battle or something like that. All right, now let's get to our actual question. We want to know, what is the effect of willpower above and beyond strength and superpower in predicting whether you died in the final Avengers battle? And so we're going to fit a full and a reduced model. So like I said, we can look at visuals. We can look at model comparisons, which is what we're going to do now. Might as well visualize it first, because why not? I always like to gather as much information as I possibly can. So that may mean looking at multiple visuals. And so here we've got a visual model comparison between the two. So that greenish bluish line right there shows the prediction of the reduced model that says a flat line because we don't have willpower in there. So it's basically, it should be flat. If it isn't, then we got problems. And then we got the full model, which is the red line, and it's saying that there's a slight difference between them. So we're seeing different predictions, but they're not vastly different. So like the willpower prediction for somebody who's at approximately 125, this one is probably 10, this one is probably 15. So maybe like a 5% difference in prediction. Now let's go ahead and get to the model comparison metrics. And like I said, we don't get R squared or adjusted R squared or anything like that, but we do get some other things that we don't get otherwise. Let me make that bigger. There's the accuracy table, so it basically uses both models, the full and the reduced, to predict who dies versus who doesn't and sees how accurate they are, or how good the sensitivity, specificity, positive predictive value, all those are. Problem is, if you've got a data set like this where the number died is small, it's like 10%, these aren't very informative. So, and in this case, they're very similar, so they're basically saying they're not all that different. But we can't look at the AIC, BIC, base factor, p-value. So the AIC is favoring the full model, BIC is favoring the reduced model. So is the Bayes factor, and the p-value says they are not statistically different, in which case you should go with the reduced model. So everything but the AIC says we don't need willpower. And then down here we got predicted differences between the two models. So on average, technically on median, they only differ by 1 percentage point in their predictions, but the maximum they differ is about 10%. The minimum they differ is that they are precisely estimating the same value. So those are model comparison metrics. And so we got the visuals that say we've got it's not a very steep line. And then we've got the model comparisons telling us the evidence seems to suggest that maybe willpower isn't all that much. The only exception to that is the AIC. Now, what about estimates? All right, now we get to the core problem with logistic regression. So I'm just going to output the estimates here, and then all T does is it transposes it. It basically flips the rows and the columns. And the reason why I did that is if I just look at estimates 2, it'll show it all in one line, and I want them stacked because visually I prefer that. Doesn't really matter what I'm doing. I'm just giving it a good way to look at it. All right, so let's go ahead. So this estimates function is from the flexplot package, and so I just made some notes so that we could interpret what's going on here. Let's see, can I get those? Ugh. Okay, yeah, maybe my screen is big enough you could still see it. All right. So, looking at the estimates, we got the raw coefficient. What does that 0.009 mean? That means, and I'm going to read it because if I don't read it, then it's likely that I'll mess something up, because all these are kind of mental tongue twisters. Did I just make up a term? That's cool. If it is mental tongue twisters, does that make sense? I don't know, but I like it. So all these are like difficult to wrap your head around, basically, is what I'm trying to say. So that 0.009 says that every minute you spend waiting at the DMV increases the log of the odds of dying by 0.352. Or in other words, if you're thinking about a slope, every unit increase in x means this many increases in y. It's the same thing, but instead of in y, it's in the log of the odds of y, or log of the odds, which is the probabilities, or the log of p divided by 1 minus b. Now, I don't know. Now, chances are you're like, WTF, dude. I don't get it. And I don't either. So, good job. You are in good company. I do not have an intuition for the scale of log of odds. I'm not mathematically savvy enough to be able to look at that 0.009 and know exactly what it means. So that first one isn't all that helpful. Let's go on to the next one, the odds ratio. And that's a little more interpretable, but still requires some mental gymnastics. Now let me just review what an odds means. So when you're talking about an odds, a lot of us might think of like gambling. So if your odds of winning are 2-to-1, that means you are twice as likely to win as you are to lose. Or if you want to think about it in terms of probability, it's probability divided by 1 minus probability. So let's say my probability of winning at a game is 60%. What are my odds? It's going to be 0.6 divided by 1 minus 0.6 or 0.4, which is 1.5. That's what an odds is. So what we can do is we can take the raw coefficient, in this case 0.009, and we can exponentiate it, or basically do e raised to the 0.009. And what that will give is that will give us a odds ratio. Okay, let's think about that for a minute. So an odds is a ratio of probabilities. So now we're talking about an odds ratio. or a ratio of ratios. So it might look something like this. So let's talk in terms of probabilities. Maybe at blackjack table A, my probability of winning is 0.6. Or my odds of winning is, again, 0.6 divided by 0.4 is 1.5. Now, let's say at this other one, table B, my probability of winning is 0.55. And so my odds of winning at that table are 0.55 divided by 0.45, or 1.22. That's my odds of the other table. So now when you do an odds ratio, you divide one by the other. And so if I want to see the odds in favor of table 1 over the odds in favor of table 2, what I would do is I would take that 1.5 and then divide it by 1.22, which gives me an odds ratio of 1.227273. So that's what an odds ratio is. And what is the ratio? What relative to what? So in the first example, I talked about table A versus table B. What does it mean in this situation? Well, it means how do your odds change as you increase by 1 point on the x-axis? So in this example, we're talking about waiting times. And so let's pick an arbitrary value because the odds ratios change consistently at a consistent rate throughout the entire curve. And so let's say you're just randomly, we're going to compare those who waited for 40 minutes versus those who waited 41 minutes. Just because it's a 1 unit increase. We could have done 20 and 21, or 1 to 2, or 5 to 9, or 5 to 6, or whatever. And so what the odds ratio tells you is they reflect the degree to which your odds change as you go from 40 to 41, or from 1 to 2, or whatever. Now with that, let's step back into R and look at what this means. 1.009, that tells you the odds of dying for those who wait 41 minutes is 1.09 times higher than the odds of those waiting 40 minutes. That's what an odds ratio means. So that's not very intuitive to me. You're talking about a ratio of two probabilities. I understand probabilities pretty well, and I understand odds pretty well, but once you get to another level, it's just like, it's not easy to say. But what you could think about it, which is a little bit easier, is we could say that every minute you are willing to wait, your odds increase by 0.9%. So that's what an odds ratio means. Again, if you're like me, you have to do some mental gymnastics. What was the term that I used earlier? Mental tip of the tonguing? I don't remember. Anyway. So yeah, that's the odd ratio. Now we got this other thing. This is, again, in FlexPlot, the inverse odds ratio. What is that? So far we've been talking about what is the probability of dying. We could also talk in terms of what is the probability of living, because I find it easier to interpret odds ratios that are over 1 and not as easy to interpret odds ratios that are less than 1. And so 0.991 means the odds of living decrease by about 1%, which is 1 minus 0.991. That's 1%. The odds of living decreases by about 1% every minute you are willing to wait. All right, and then now we get to the standardized odds ratio over there. See, the problem with odds ratios is that they are, well, it could be problematic. Might be exactly what you need. You can't compare them across variables. So you can't compare, for example, the odds ratio of willpower changes versus the odds ratio of strength changes, or the odds ratio of dollars in the bank account, or the odds ratio of number of centimeters your bicep grows, or whatever. You can't compare across different variables with different metrics. If you wanted to, then you'd have to convert them to a z-score first. So that's what that one is. That standardized odds ratio basically converts that variable to a z-score and then uses that z-score to then make the inference. So what does that mean? That 1.172, that tells you that as you move from, for example, a mean to one standard deviation above the mean, your odds increase by 1.172. Or you can say every time you increase by a standard deviation, your odds increase by 17%. And then we get the same thing with inverse standardized odds ratio. Now it's talking about the odds of living instead of the odds of dying. And the last one, prediction difference. That was my earlier attempt to make more sense of this. It's not talking about odds anymore. It's talking about probabilities. So it says, all right, let's compare those who are one standard deviation above the mean in willpower versus those who are one standard deviation below the mean, and compute the difference in their predicted probabilities. So this tells you that it's only a 3% difference. So the people who are one standard deviation above the mean, for example, they have a 3% higher chance of dying than those who are one standard deviation below the mean. So that's pretty intuitive. And so all those were for numeric variables. Let's go ahead and look at how it might look for a categorical variable. So I'm going to just show the entries for the categorical variable. Make my text a little bit bigger now. So we've got these right here. So 1.654, again, that's on the log odds scale, which I have no intuition for whatsoever. So I'm going to skip it. Instead, I'm going to go to the odds ratio. And what does that tell you? That tells you the odds of dying for superheroes is 5.2 times higher than the odds of dying for non-superheroes. That's a little easier to interpret because you're not thinking about every unit increase causes a change in odds. It's instead just from one to the other because we only have two categories. And then the inverse odds ratio is, again, looking at the odds of living for superheroes relative to the odds of living for non-superheroes. And then we standardized. I don't think that even makes sense. And I'm not even sure why it's there. But you can look at the prediction difference. So that basically shows you the raw probability difference between superheroes and non-superheroes. So superheroes have a 26% higher probability of dying than non-superheroes. We can see that earlier when we computed these, that 0.362 minus 0.097, that's going to give you a value of about 0.26. So that's fun. So let me review some of the problems when you're interpreting estimates with logistic regression. The biggest problem is it requires some mental gymnastics to try to figure out what's going on. You have to think about odds. Like probabilities are pretty intuitive, but then you have to think about odds, and then you have to think about ratios of odds, and that just gets complicated. Another problem is that they are scale dependent, and so you can't compare them across different scales, which, again, that's fine. And another problem is that they only give the interpretation of the slopes. So notice that we didn't even talk about the intercept at all. And in regression, the intercept has an intuitive explanation, an intuitive interpretation. It tells you the predicted value of y when x is equal to 0. But in this case, it's not intuitive, and how you would interpret it is it gives you the average of the log of the odds when x is equal to 0. I don't see that as very intuitive either. All right, I'm going to pause there because this video is way longer than I anticipated it would be. So next week I'm going to introduce some new coefficients that I've developed for logistic regression that I think makes things a lot more intuitive so you don't have to interpret odds ratios. So if you're interested, be sure to tune in next week. So I hope you found that helpful. If you are interested in meeting with me, I just recently started doing consulting. You can schedule an appointment with me. And I've left a link in the description for that. I also offer live classes, so you get to interact through Zoom with me, and we're doing a visualization and a machine learning course. It's kind of 2-in-1 starting in May. It's going to be Tuesday, early afternoons from noon to 2 Eastern Standard Time, which is like New York City time. And you could also do a self-guided class where you go at your own pace, and you can still ask me questions. It's just through the online forums there. So I hope to see you there. Let me know if you have any questions or comments, and I'll see you next time. Peace out.